Yes, welcome back dear students to the tutorial about the chemical applications of group theory. This is the second video in this series. First we are discussing about the application of group theory in spectroscopy. Okay, in the first video we had discussed about the different vibrational modes of water molecule. Okay, that is first we have calculated the total character. Okay, first we get a reducible representation. On reduction we get a irreducible representation, a group of irreducible representation, and that is a total character. That means it include all the vibration, all the degrees of freedom, translation and rotation. By subtracting translation and rotation, translation mode is obtained from the character table of C2V point group. That is, X is the translation, means X direction, transformation in translation X direction, B1, Y direction, B2, Z direction, A1, and rotation X direction, B2, Y direction, B1, Z direction, A2. And that is gamma translation is equal to translation degrees of freedom is equal to A1 plus B1 plus B2, rotation degrees of freedom A2, B1, B2. On subtracting we get 2A1 plus B2. Okay, that is the vibrational degrees of freedoms of water molecule are 2A1 plus B2. That is among the three vibration degrees of freedom of water molecule. Symmetric stretching mode is actually A1. It transforms as A1. That is all the operation, all the symmetry operation has no effect on the symmetric stretching. Therefore, it is a A1 vibration. And symmetric bending also a symmetric type structure. Therefore, no change in the symmetry operation. This is also A1. And asymmetric stretching, the characters, that is in the last video, asymmetric stretching C2 E character is 1, C2 character is minus 1, sigma V minus 1, sigma V dash 1. That is 1, 1, 1, 1 minus 1 minus 1, 1. That is actually anti-symmetric stretching. That means it is B2 mode. Okay, that is the anti-symmetric stretching mode is B2. And this was the last video we had discussed. And now in this video we will discuss about the among the three vibrational modes of water molecule, which are infrared active and which are Raman active. Okay, the transition probability of this mode in the infrared and Raman spectrum. And first we will discuss the identification of infrared active vibrations. We are taking water molecule as example. And you have studied in spectroscopy that the equation to predict the spectral transition probability is P is proportional to integral minus infinity to plus infinity psi I P cap psi f d tau. Okay, and the P is this P cap is called the transition moment integral. P cap is transition moment integral. Okay, a vibration mode will be IR active if the vibration, and that is you have studied, that is if a vibration mode to be IR active, the vibration brings about a change in dipole moment. Only those vibration which brings about a change in dipole moment is IR active. That is we have studied even the UG classes. Okay, therefore this P in IR spectrum, hence in IR P is actually dipole moment operator. Okay, actually it is a transition moment operator. In the case of vibration spectroscopy, this P cap is actually dipole moment operator. And you know that P cap is equal to, that is we can return as mu, is equal to mu 0 d mu by dq, q equal to 0, q, where mu is the dipole moment at any instant. Okay, and q a coordinate indicating displacement during vibration. Q is a coordinate that indicates displacement during vibration. and mu 0 is the equilibrium dipole moment, and d mu by dq is the rate of change of vibration, and this dipole moment can be resolved into three components: mu x, mu y, mu z. Mu x, mu y, and it is mu z. And each component can be represented by a similar equation written earlier. That is, mu x is equal to mu x 0 d mu by dx, x equal to 0. For q, here we get x into x. Okay, similarly for mu y, we can write like this: mu y is equal to mu y 0 d mu by dy, y equal to 0, y. Similarly for mu z, we can write similar equation: mu z is equal to mu z 0 d mu by dz into z is equal to 0, z. Okay, so we can get three transition moment integrals, and the probability the probability p also has three components. Okay, that is, px is proportional to integral of minus infinity to plus infinity psi I mu x psi f d tau. Generally, we write p equal to proportional to psi I mu psi f d tau. For px x direction, mu x d tau. For py, similarly we can write it is proportional to integral of minus infinity to plus infinity psi I mu y psi f d tau. Similarly, like we get three transition moment integrals. Okay, so for a transition to be IR active, any of this should be non-zero. That is, px, py, or pz. Any of this one will be non-zero. The probability, the transition, that mode will be IR active. There is a probability of transition. That is, the probability p is the sum of px plus py by pz. That is, the total probability p is the sum of px plus py plus pz. Okay, if at least any one of this is non-zero, this total probability become non-zero, and the transition probability occur. That means that mode will be IR active. If no transition occur, if px is equal to py is equal to pz is equal to 0, that is, if all the integrals are 0, then that transition never take place in IR. And px can be written as integral of minus infinity to plus infinity psi I mu x psi f into d tau. We already told you. And now, what is this mu x? Mu x is equal to mu x 0 plus d mu by dx into x is equal to 0, x psi f d tau. Okay, here this mu x 0 and d mu by dx x equal to 0 are constant, so they can be taken outside of integration. So we get mu x 0 integral of minus infinity to plus infinity psi I psi f d tau. This term will be 0 because psi I and psi f are orthogonal wave function. Wave functions are orthogonal, therefore two wave functions are orthogonal, therefore psi f and psi phi. Integral of minus infinity plus infinity psi f d tau is equal to 0. This term becomes 0. And d mu by dx x is equal to 0. Integral of minus infinity to plus infinity psi I into x into psi f into d tau. Okay, and then since d mu by dx is a constant, we can now write the px is proportional to integral of minus infinity to plus infinity psi I x psi f d tau. Okay, and this is our equation. We want to evaluate actually this integral. Okay, px proportional to minus infinity to plus infinity integral of minus infinity to plus infinity psi I x psi f d tau. We can evaluate this integral by knowing the symmetries of psi I x psi f. Okay, symmetries of psi f we can obtain from the character table. Symmetry of x can be obtained from the character. Symmetry of psi f can be obtained from the character table. And from that symmetries, we want to find out the direct product of these three symmetries. That is symmetry of psi I, symmetry of x, symmetry of psi f. From this direct product, we can evaluate this integral. And here psi I and psi f are the represent initial and final vibrational energy level. Psi I is the initial energy level, vibration energy level. Psi f is the final vibrational energy level in which the transition occur. Transition occur from psi I to psi f. Psi I is the lower vibration level, psi f is the higher vibration level, or it is the initial level, it is the final level. And you have studied in mathematics that consider an integral of the type integral minus infinity to plus infinity fx dx. It will be 0 if f is an odd function and non-zero if it is an even function. Okay, I think you may remember this thing in mathematics. That is, an odd function means f of x is equal to minus of f of minus x, and an even function is f of x is equal to f of minus x. Okay, if f of x and f of minus x are equal, then it is called an even function. If f of x is equal to minus of f of minus x, it is called an odd function. For example, x square. Okay, it is an even function because, for example, if x is equal to minus 2, then minus 2 square and plus 2 square, both are equal. Therefore, x square is an even function, but x is an odd function because minus x is not equal to x. Okay, and you have studied in mathematics that if f of x is an odd function, the integral will be 0. If it is an even function, it will be non-zero. Even function means it is a totally symmetric function, or the symmetry will be totally symmetric. That means, that is, if a function is an even function, okay, then if a function is an even function, then the symmetry of that function will be a totally symmetric function, symmetry, that is A1 mode. Okay, that is, in general, the value of integral will be non-zero. Value of this integral will be non-zero if the integrand is totally symmetric. That is the main point. The value of this integral of psi I x psi f d tau. Similarly, for py, we can try psi I y d psi phi d tau, and z we can try psi I z psi f d tau. And any of this integral, if it is non-zero, transition will takes place. Okay, and to be non-zero, the direct product of these three symmetries should be a totally symmetric one. Okay, that means for a vibrational, to predict for a vibrational mode to be IR active or not, we want to evaluate this integral px proportional to integral of minus infinity to plus infinity psi is x psi f d tau. Okay, and this can be evaluated as by knowing the symmetries of psi I, psi f and x. Similarly, for pz, py, symmetries of psi I, psi f and y. For pz, psi I, psi f and psi z. And we can easily ascertain whether the integrand is totally symmetric or not. If we know the symmetries of psi I, x, psi f, we can easily predict that integrand is totally symmetric or not. Okay, how we know the direct product? Okay, we have already studied how can we carry out a direct product. Okay, then we will study later. Okay, we can come to the water molecule as example. In the case of water molecule, the symmetry species of normal modes are 2a1 plus b2. Okay, the actual symmetry of a vibrational level can be obtained as follows. That is, we have three vibrational modes: symmetric stretching, asymmetric stretching, and symmetric bending. And the symmetry of these modes are A1, symmetric stretching is A1 mode, symmetric bending is also A1, asymmetric stretching is B2. Okay, and each mode, listen carefully, each mode have different level. For example, for symmetric stretching mode, there is the ground level and first excited level, second excited level. Okay. For also for asymmetric stretching, there is ground level and second level, first level, first excited level, and second level, and so on. Okay, and transition is actually taking place from the ground level of one mode to the first excited level of that mode. Okay, and symmetries of the levels are not all equal. Okay, can you understand me? Listen carefully. That is, for example, symmetry of vibrational levels of the vibrational mode which transforms as B2. That is, asymmetric stretching is B2. And symmetry of the different levels of B2 or asymmetric stretching is actually B2 raised to nu. B2 raised to V, actually it is V, where V is the vibrational quantum number. That means for ground level, the symmetry is B2 raised to 0. That is, B2 raised to 0 means actually it is an A1 mode. It's totally symmetric. That I will show you. Okay, for first level, it is B2 raised to 1. That is B2 itself. For second level, it is B2 raised to 2. B2 raised to 2. Then we want to, that is B2 into B2. We want to calculate the direct product of B2 into B2. What will be the symmetry of that level? Okay, can you understand me? Okay, that means I will explain more. That is, similarly, we can set the symmetry of any vibrational level of any vibrational mode. Okay, can you follow me? That is, for each mode, there is ground level, first level, second level, like that. Okay, and for each level, the symmetries are different. That is calculated by this equation. That is, for a particular mode, there is a symmetry. That is raised to its vibrational quantum number. For say, ground level, V equal to 0. First level, V equal to 1. You will understand by consider this example. For example, in the characters of B2 is 1, minus 1, minus 1, 1. From the character table, we can see that character of B2 mode is 1, minus 1, minus 1, 1. And for ground vibrational level, that is B2 raised to 0. Okay, to get ground vibration level of B2 mode, that is asymmetric stretching mode, we want to calculate B2 raised to 0. That is, characters are 1, minus 1, minus 1, 1. That is 1 raised to 0, minus 1 raised to 0, minus 1 raised to 0, 1 raised to 0. And any term raised to 0 is equal to 1, we get 1, 1, 1, 1. And these characters are those of A1. Okay, so for any mode, okay, for example, if in the case of another mode, for example, it is whatever be the mode, we get equation like this. Okay, or the characters raised to 0. Any character raised to 0 is equal to 1. Therefore, it is very important point, the ground vibration levels of any mode is totally symmetric. Okay, that is psi I is always totally symmetric. Psi I is the initial mode, initial level. That is ground. Initial level is always ground level. In vibration spectroscopy, you might have studied that transition is the mainly occurring from the ground level to first level. Okay, I think you might have remembered that in vibration spectroscopy, all the molecules are in ground vibration level first. So the most intense line is, or most intense transition is from the ground level to the first level. So psi I is the ground level, that is V is equal to 0, and that level is totally symmetric, that is A1 in all vibration mode. Okay, that is psi I. This is very important point. That is psi I is always A1, whichever be the mode. Modes are, in the case of water molecule, there are 3 modes, 2A1 plus B2. Okay, even in the B2 mode, that is asymmetric stretching level, the ground level is A1. How it is obtained? For ground level, B2 raised to 0 had to taken. Then B2 raised to 0, that is this character is 0 equal to 1 1 1 1 1, that is A1 mode. That is for ground vibrational level of any mode is a totally symmetric one, that is A1 mode. Can you understand? And the psi f is the first excited state, nu equal to 1. I told you in vibrational spectroscopy transition is always from nu equal to v equal to 0 to v equal, this is actually v to 1, that is from ground level to the first excited level. That is the 99% intense transition, because in vibrational molecules, we can population, by studying the population we can see that all the molecules are in ground level, vibration level, in normal temperature, normal condition. Therefore the most intense, most important peak is from nu equal to v equal to 0 to v equal to 1. V equal to 0, that is psi I, and that is always totally symmetric, we have studied. And psi f is the first excited state, that is v equal to 1, have symmetry of the vibration mode itself, that is a term raised to 1 is equal to that itself. For B2 mode, B2, that is asymmetric stretching, the psi f is actually B2 raised to 1, that is first level, and that is equal to B2 itself. Can you understand? That is the psi f has the symmetry of the mode itself. For B2 mode, psi f is B2 itself. For A1 mode, psi f is equal to A1 raised to 1, that is A1. Okay, there is symmetry of the final level, that is the excited level, nu equal to 1, has the symmetry of the mode itself. What is the mode? It itself. For example, for symmetric stretching, psi f is equal to A1, because symmetric stretching mode is A1 mode, psi f is A1. Psi I in this case also A1. For symmetric bending, psi f is A1 and psi I also A1. And unsymmetric stretching or asymmetric stretching, psi f is equal to B2, because its mode is B2, B2 raised to 1 is B2, but psi I is A1, because psi I is always A1, whichever be the mode. Okay. So now we want to discuss about the IR transition probability of different modes. Okay, we come to the point. IR transition probability of symmetric stretching and symmetric bending, both are A1 mode, both are A1, symmetric stretching and symmetric bending. So we want to calculate the transition probability Px, Py, Pz. If any of this one, either Px, Py or Pz, if any of this one is non-zero, this mode will be IR active. Okay, first we calculate Px. Px is proportional to integral psi I x psi f d tau. Okay, psi I told you A1 mode, psi I is A1. And x, what is the symmetry of x? That we can obtain from the character table. Okay, by looking the character table of C2, you can see here. Okay, x, can you see? Yes, okay. What is symmetry of x? Here, x, character table of C2 is this one, x is here, x is B1 mode. So psi I is, psi I is A1 and x is equal to B1. And psi f for A1 mode, psi f is always the symmetry of the mode itself. For A1 mode, psi f is equal to A1. And A1 into B1 is equal to B1, B1 into A1 is equal to B1. It is not totally symmetric. Okay, therefore the direct product is not totally symmetric, therefore Px is 0. It is an odd function, not an even function, that is Px is equal to 0. Now we calculate Py. Similarly, psi I is A1. Psi I initial wave function is always A1, whichever be the mode. And y, look at the character table, y is B2, so it is B2. Into psi f is for A1 mode, it is A1 itself. And A1 into B2 into A1 is equal to B2. Okay, Clear? See, because multiplying any symmetry with A1 will be that symmetry, because A1 is always characters are 1. 1 into 1 into 1 into B2 is B2 itself. Therefore, it is B2. B2 into A1 is equal to B2. It is also not totally symmetric. Py is also equal to 0. Now Pz. Okay, psi I is equal to A1 and Z is equal to A1. Okay, so A1 into A1, psi f is also A1, A1 into A1 into A1, A1. That is totally symmetric. Therefore, Pz not equal to 0. So the total probability P equal to Px plus Py plus Pz not equal to 0. So these vibrations are infrared active. Okay, that is symmetric stretching and symmetric bending are IR active. Yes, okay. Now we will discuss about the IR transition probability of anti-symmetric stretching. Symmetric stretching and symmetric bending are IR active. Now we will discuss about the anti-symmetric stretching. Again, Px is proportional to integral of minus infinity to plus infinity psi I x psi f d2. Psi I is equal to A1. Initial mode is always E1. Ground level is always A1. Then x here is B1. X is B1. Okay, into B1. Psi f B2. Okay. A1 into B1 is equal to B1 itself. B1 into B2 you can calculate by direct product method. B1 into B2. 1 into 1 is equal to 1. Minus 1 into minus 1 is equal to 1. 1 into minus 1 is equal to minus 1. Minus 1 into 1 is equal to minus 1. So 1, 1, minus 1, minus 1. Yes, 1, 1, minus 1, minus 1. This is A2 mode. A2 is not totally symmetric. Here A1 is the totally symmetric. Totally symmetric means all the characters are 1. Only A1 mode is totally symmetric. A2 is not totally symmetric, therefore Px is equal to 0. Okay, and Py, this is actually Py. It is proportional to integral of minus infinity plus infinity psi I y into psi f into d2. And psi I is equal to A1. Psi I is always A1 and y is equal to B2. Sorry, B2 into psi f is equal to B2. B2 into B2 is equal to A1. You have studied by while we are discussing about the direct product. The direct product of two same symmetry are always A1. Okay, direct product of same symmetries, same irreducible representations are always even. B2 into B2 is always equal to, yes, B2 into B2 is always equal to A1. And B1 into B1 is equal to A1. B2 into B2 is equal to A1. A2 into A2 is equal to A1. Direct product of two same symmetries are always totally symmetric, A1. So B2 into B2 is equal to A1, A1 into A1 is equal to A1. Therefore Pz not equal to 0. Okay, sorry, it is actually Py not equal to 0. Therefore, this band is IR active, because if Px, Py, Pz any one if not equal to 0, then that mode will be IR active. Therefore, anti-symmetric stretching is IR active. That means in water molecule, all the three vibrational modes are IR active. Okay, then we can conclude, this is our conclusion, since psi I is totally symmetric, that is A1, the total symmetry of Px, Py, Pz is decided by symmetry of x, y, z and psi f. And we can say that only if psi f and any of x, y or z have same symmetry, their product will be totally symmetric. I told you, we get totally symmetric representation by the direct product of same symmetry. So we can say, if psi f and any of x, y or z have same symmetry, their product will be, direct product will be totally symmetric. And P become not equal to 0 and the mode will be IR active. That means we can conclude like this. A vibrational mode will be IR active if the normal mode belongs to the same representation as any one of the Cartesian coordinate. Okay, that is I told you psi I x, y or z into psi f into d tau. This is our integral. Then psi I is always A1. Okay, so to get this product, that is psi I x, y, z, x, y or z into psi f, direct product is to be A1. This x and psi f should have same symmetry. Then only the product of this to become A1 and A1 into A1 become A1. Okay, if x is equal to B2, then psi f also should be equal to B2. Then only B2 into B2 is equal to A1, A1 into A1 is equal to A1. Or otherwise we can say that if psi I is equal to psi I is always equal to A1 and y is equal to, suppose another symmetry, I am saying that it is B1. Then psi f also should be B1. Then only this B1 into B1 is equal to A1. A1 into A1 become A1, totally symmetric. The integrand totally symmetric. The product and the it will be non-zero. Integration will be non-zero and the mode will be IR active. So this is our conclusion. And this psi f is the mode of symmetry of psi f is the symmetry of the mode itself. I told you. Okay, so we can conclude a vibrational mode will be IR active if the normal mode belongs to the same representation as any one of the Cartesian coordinate. Okay, psi f is the symmetry of normal mode. So the symmetry of psi f, that is a normal mode, should have same symmetry of any of x, y or z. Can you understand? I am told you one more time. That is psi I into x, y or z into psi f into d tau. Okay, psi I is always A1. So to be totally symmetric, to be IR active, this psi f, that means psi f is the symmetry of the vibrational mode, and any of x, y or z should have same symmetry. Then only this become totally symmetric and integrand will be non-zero. It will be IR active. So a vibrational mode will be IR active if the normal mode belongs to the same representation as any one of the Cartesian coordinate. Look at the character table of C2V. Okay, the consider A1 representation. The symmetry of A1 and Z coordinate are same. Therefore, A1 will be IR active. And X and B1 are same representation. Or X, B1. So B1 will be IR active. B1 mode will be IR active. And Y, B2. B2 mode will be IR active. But A2 mode, if in the C2V molecule, if there is an A2 vibrational mode, it will never be IR active because any one of the Cartesian coordinate belongs to A2. Okay, any one of the Cartesian coordinate belongs to A2, therefore A2 mode. In the case of water mole, there is A2, there is no A2 mode, but in some other C2V molecule, there are many examples. If there is an A2 mode, vibration mode, it will be never IR active because it is not belongs to any of X, Y or Z. Okay, another example, if you take C3V character table, you can easily say which modes will be IR active. Just very simple, very simple. Look at X, Y, Z. Z A1. A1 mode belongs to Z. Therefore, A1 mode, if there is an A1 mode of vibration, it will be IR active. Okay, and E mode, E, X and Y belongs to E. It will be IR active. But A2 never IR active because it does not include X, Y or Z. That's our conclusion. By simply looking the character table, the modes belongs to X, Y, Z will be IR active. Okay, only look at this area and this area. X, Y, Z. Look at the X, Y, Z. Okay, modes belong to X, Y and Z coordinates will be IR active. Okay, and modes which do not belongs to any of the Cartesian coordinate X, Y or Z, it will be never IR active. That is our conclusion. Okay.